So maybe it would be nice to summarize a few things from the paper before we move on and try and explore some further things about networks. So I'm going back to the definitions because I think there are some things we're going to see again and again, and if you keep reading about networks or other things, there's sometimes there's a confusion in the literature because, as in many things that are growing rapidly in different fields, people use different names for the same thing. So networks and graphs are often used interchangeably. You can use one or the other. Some people prefer the word graphs for a mathematical description of a network, which they would define as the real thing that connect the model of the system, the connected nodes. Others, they use the both words. So mostly in mathematical literature, you would see networks mentioned as graphs. Same holds true for nodes are called vertices, and edges are called edges. So for now, I'm using everything, whichever is more convenient. We can strictly define a network or a graph as an object, and it's usually most often symbolized by G, and as a collection of vertices and edges. So we can vertices are usually symbolized by V, and E are the edges. So this is a way in which we model many different systems. The V is as V we usually call the set of all vertices. So we could write those as V G, let's say, a set of all vertices, and the equivalent set of all edges is E of G. This is a somewhat more formal way of building up on things, but we should always think what does that mean. An edge needs to have two vertices in connecting to vertices, but as we saw in the examples, that's not always true. And here we can start thinking of, yeah?
It's not always true that an edge has two vertices, one on either side.
So that's how, when we decide to model our system, we have to make this decision. So what is an edge and what is a node? So if we think about the networks we were looking at before, intuitively we would think that a node is a person and an edge is a connection between the persons. But maybe for the problem we care about, it's more convenient to think as a person, an edge, and not as a node that connects to ideas or things like that. So when we are mapping the system to our model, to our network, we make some important decisions about what type of network this is going to be. So before going into the types of networks, we usually have this as this set has n vertices and this has m edges, and that's just a shorthand so we can talk afterwards. So we saw mentioned a few distinctions, groupings of networks, and one, I guess the very obvious one is an undirected network, where we have nodes, as was the graph we saw, and maybe most of the examples in the paper, are undirected networks. The directed network has some extra information in it, and we can also slice the world of networks in many different ways. We can, besides the undirected and directed, some where where edges have properties, which we call weights. So in the previous example, if you know some friends and you can assign some probability to each one of those about something, this route, I think that if I send the letter to Oana, it has a high chance of going to this person than going to another person. So then we can assign weights to our nodes, and we can call this, so we can divide the possible networks into weighted networks and non-weighted networks. And of course you can have weighted and directional networks, and any combination of those. And going back to the multiple connections, we can have a network with multiple edges between two people, because if we want to model, let's say, humans, they talk to each other, but they also email, or they hug, or they handshake, or whatever. So there are many different types of relationships we could model, and then it's useful to use different types of edges.
Some edges could be directed and some couldn't.
Yeah.
To really blow your mind.
And this goes on. So you can, depending what system you have in mind, what you want to study. Yeah.
Are the links, the edges, independent of something more general? It seems to me that most networks I've seen, the links may be directed, may have properties, but they're not, those properties are not dependent on other things, the use of that link outside of the communication to the next guy. So can I have a link which changes whether I'm going to use it to communicate to this guy versus this guy?
So you mean you're changing the link?
Changing the link's characteristic because of the way I use it.
I think this what you're going after is what model to use. If in our system the link does change, we would use a weight that does change through time, or in which direction you go. Is that what you...
Also, what you're talking about is a dynamical process where the links are being updated somehow, right? They're changing.
And they're changing because this link, I'm communicating to this guy.
So
But this guy, the link to this guy has a different weight if I communicate to this guy in order to communicate to this guy versus...
This week, all of the networks
this
you're
one.
looking at are static. They're like frozen in time.
Okay.
Next week, we'll talk about dynamics on networks.
Okay, thanks.
Although
Sorry.
this is not a
I
time
don't mean to
dynamic.
hold up the chart.
No, that's the most important part of the class. Just always
Well,
ask questions and...
Is that what you mean?
discuss.
Do you mean that there's sort of an active process going on and that's why the links are changing between nodes?
I would even more generalize. I can see the characteristics of the links changing
So this would be a function of where you go.
deterministically over time.
Right.
But I'm really getting further, is the characteristics of that link going to depend on
Where the message
other
is going.
things outside of those two
So then the
things?
weight would be a function of whatever.
If I want to send a
Yeah.
message to Barack versus Romney.
Yeah. So
Anyway.
we are
Even
making up the model, so we choose how to do it. The hard thing is to decide which is appropriate and
Okay.
if it's
So
necessary.
it's general enough that I can make it terribly complex.
Exactly.
Fine.
And afterwards realize it was too much. When you- so we went through a few types. And when I think that there's no rule against having a link to yourself. So you could have a node that connects to itself. You could talk to yourself, yes. Depending on the
You don't want to be the node that just has a link to itself.
So what other things are characteristics of here? So let's move on to some properties of graphs. We can divide the properties of graphs, the ones that are mentioned here, but in general what we would like to know about a network in two broad groups. One are the global ones, as the diameter that we discussed before, and the other ones are the local ones, just by looking at a single or a small neighborhood. So one that we already mentioned is the degree of a node, which is how many connections this node has. Because in the case of the directed network, we have two different kinds of edges. We need to have two different kinds of degrees. So if we can draw some random network, from something like this. Here we define the degree of our node. One, let's say, we call this 1, 2, 3, 4. We define it as the total number of edges. But specifically for this type of networks, we need two degrees: the in degree and the out degree. So, is this super obvious if I ask somebody to say what is the in and what is the out degree of here?
It's out 2 and in 0. In is 0 and out is 2.
Yeah. So it's easy to see how this works. This is a local property, so it's a property of the node. If we have a network, we can look at all of them together at the same time and study their distribution, and this could tell us something about the network. One thing I forgot to say. So here we have in degrees and out degrees, but also this definition, the overall degree still has some sense. So we can still talk about the degree which overall is 2, which is the sum of in and out degrees. There's a different set of information we learn from each. So we'll skip for now the degree distribution. We'll come distributions of degrees. We'll come back to those later on. Let's have a look at the more global property of a network. So let's make this a bit larger. Another property that is often useful is the eccentricity of a network. And this is defined again for a node. And this is defined as the maximum distance from this node to any other possible nodes in the network. So let's make this a non-directed network. So imagine this is the outline of the building. We could have doors that connect to rooms, and these are edges, and each room is a node. And we want to find the location for the kitchen or the toilet that is central enough. Here we're looking for a node where you can get there from any other possible node really fast. And to do this, we use the eccentricity of the network. So, does somebody want to try and calculate it with me? Let me repeat the definition first. The eccentricity of a node is its maximum distance from the set of all possible distances with other nodes. And again, when I say distance, I mean the minimum distance. Does somebody want to try and, for this small example, 5, try and see if we can figure it out?
For every node?
Yes.
Yeah.
How would I go and calculate this?
For example, if it was 1, will you just count the distance between 1 and 2, 1 and 3, 1 and 4, 1 and
Yeah.
5, and take the maximum?
Yeah. So here this is
2.
and so we don't mix the numbers and the node names. So this was 2. How much? What's the eccentricity of this?
2.
So again, this,
2.
this.
3.
So where we would place?
Missing one.
That's symmetric.
What?
You 3, you just didn't write down.
Oh yeah. So if we have this floor plan, we can choose where to place the emergency. If it's a city plan, it would be the hospital, let's say, the city. So we can choose one of these 3. So do you see why this is a global property of the network? If we add something, we expand the city, adding something here, we have to readjust everything. Well, if these were degrees, we wouldn't care about this.
Would you take the average if you wanted to represent the whole graph? Like if it's a global property, you should speak about the whole graph. Right?
Yeah, this will tell us something about the property of the whole graph. The average eccentricity, I'm not sure how meaningful it is, though. It could tell you how closely connected is in a sense.
Mm.
That's
but I
the
can think of-
degrees of
Yeah,
separation.
I can think of any.
Yeah.
Yeah.
Is taking averages in these cases usually helpful, or do you really need to look at, as you said, for the degree You talked about the degree distribution. Didn't you talk about like average?
For this
degree
particular
as well?
measure, I don't see where we could use an average.
But just in general, for these different
For-
measures on networks, would you
I-
generally recommend looking at the whole distribution, or when
It's
is it
always better to look at the
average?
distribution.
Maybe someone can try to argue for that based on things we talked about last week. You all should be able to answer that question. Based on what Ken said today and based on what we did last week.
If the degree distribution follows a power law, then the average is somewhat meaningless.
Yeah. So we, a lot of things follow power laws. The averages don't mean a whole lot there. Or they don't tell us anything. Which I imagine, for this simple network, there's probably no power law behavior. But in a real network, if the average of eccentricity, it's probably meaningless. You're probably more interested in like the maximum value.
But we have a degree of separation constant, right?
Yep.
Now, that translates into a pseudo-average centrality.
It's all the word pseudo. It's not exactly the same.
It's not the same. So how do I go from the centrality numbers on each node to determine that sort of degree of separation number?
Well, I can leave that as a homework exercise for
Okay.
you.
Okay.
One important thing is that
That's 6, isn't it?
But he just
What
told
is
me
that
mean
estimate?
doesn't mean anything in a power
Depends on
law
what
with
the
lots of
estimate is,
things.
It sounds to me like if we're looking at degree of separation, we will also look at, we want to look at the relationship between each node and every other node, so we would just take the maximum, for which we take for
It tells you
calculating
if it's high enough
centricity.
or low enough or something.
But we would look at every distance between this node
Right,
and
so
every
if
other
it's,
node.
if it's,
Then it
if
has a
it's
defined.
a defined mean,
So-
but it still doesn't tell you any characteristic property of the.
yeah,
We were talking about the diameter earlier, right?
Mhm.
So
I think then it converges to that.
just be max
No, your
eccentricity.
sample gets bigger.
Let's get a
Oh,
number.
sorry.
But that
We have two
doesn't
discussions
tell you
going on at the same
that
time.
doesn't represent a typical size.
Sorry.
yeah, go on. And we can come back to
So when we were talking about diameter earlier, is that just the maximum eccentricity of all of the set of all eccentricities of the set of all of the node's eccentricities?
the diameter.
Eccentricity.
Centralness, isn't it?
Eccentricity.
Eccentricity.
Exit.
Yeah.
Okay.
When we were talking about
Eccentric.
the diameter.
The diameter is the maximum of the largest distance.
Mhm.
Which is this number.
Yeah, I guess, yeah, so the diameter should be the largest eccentricity. Yeah. And there was one other thing going on?
But sort of more a question about last week. Yeah, the idea is, last week we talked about that some power laws have well-defined means. If they have an exponent below a certain value, and that's definitely true, but that mean still does not represent a typical size of anything. Because it's a power law, it isn't a typical size. It's a scale invariant. So you can get a number, but still not going to tell you anything that useful about the properties of the distribution.
But all networks don't follow a power law distribution, so
It's
for
scale
some
invariant,
networks,
so it can't tell you a typical scale.
Yeah,
it's just in the case for me.
and actually even if you have.
Mike wasn't here last week.
And even if you have a network that does follow a power law distribution, you can still calculate the mean and the median. It might not be useful to characterize this particular network, but for a given size of nodes, it's still meaningful. So it does have some. So you could compare two networks just by looking at the median, whatever degree, if they have the same size. But it's not as useful for whatever statistics we want to understand, or the way in which we construct the reasons why the network looks as it does. So, okay, yeah, we did talk about these two simple examples. As we said at the beginning, you can just look at the one network, eyeball it, count things, and then give an answer. But as if we want to study a more, if we want to study some more realistic networks, there are many ways of representing it that are more convenient to calculate the quantities that we are interested into. So I'm recreating this here. And one method of summarizing or representing networks is to use a matrix. So we could create a matrix with nodes and as rows and columns.
Do you need to put 6 in the middle of all of that? 6.
Yeah. So the way in which we translate this to a matrix is this is an we go through all possible combinations, and for every edge we put a 1, and for the absence of an edge we put a 0. So we can do this here. We can see 1 is connected to 2 and 6. 2 is connected to 1 and 3 and 6. 3 is connected to 2. 6 is connected to, and 4, let's do 4. It's connected to 6. 5 is connected to 6. And 6 is connected to 1, 2, 4, and 5. And the rest are zeros. We don't need to draw. So do you notice something about this matrix? Any interesting thing?
Symmetric because it's under the graph?
Yeah, it is symmetric. Why it is symmetric?
Is it because it's an undirected graph, so it's
Exactly.
from A to B, so
Mhm.
it's from A.
So if we did have a directed graph, then we would modify this. Let's go ahead and, well, no, let's give it simple. Let's try and calculate something. So we are interested in generating the degree distribution, let's say, from our friendship network or whatever. We, instead of just eyeballing it, we make matrix, and how do you think we can calculate
I'm guessing if you take that matrix is called A, you square it, that'll give you connections of degree 2. I could be wrong, but there's something.
you might be up to something. I'm interested though in the distribution of degrees.
Distribution.
So we want to find all, for each node, I guess,
Okay.
what is its degree.
Right, so you
in,
then you should
okay.
sum the columns or sum the rows.
yeah, so let's sum these. So we have 2, what's this, 3, 1, 4. Does this make sense?
Degree of each node.
Yeah, this is
Okay.
degree of each node. And this will be the distribution of degrees. In the case which is more interesting, I guess, to us of directed network, this will be an asymmetric matrix. So do you want to try and calculate one of those, or maybe we'll do an exercise afterwards for this? Yeah, we'll do an exercise afterwards. So
Wait,
let's
asymmetric or not symmetric?
what's the difference?
To me, an asymmetric is one where the off-diagonal terms are negatives of each other.
Mm-hmm.
You don't mean that, do you? What you mean is the off-diagonal terms are different than each other.
Yeah, yeah. This would correspond. We'll do an example afterwards. We'll have this, or maybe let's have a break and then do the example. So what I want to do is create a network for the class, so we can measure some things that are more fun to do. So during the break, I'm gonna make a matrix. I want to put your names, and each one of you, if you could come here and turns and fill in whoever you have from the class have talked to about something related to complexity, let's say, and then we can make a friendship network. and then let's do some statistics on this.
Let's get started, yeah.
Joel is so popular.
I know. You won't be here. Okay. First, before this is first look at let's look at the matrix representation. So. Most real networks, as we were discussing before, are not so dense as these ones. So quite often it doesn't make sense to use if we have a network of millions of nodes. It doesn't make sense to have a huge matrix. We don't have enough large enough computers. So we can. There are many alternative representations compared to the matrix we showed before. So we can just have an edge list of who is connected to who, or we can have what they call a sparse matrix, which is only the ones without caring about the zeros. But in this simple example, we have this, which is easy to look at. Do you expect this to be symmetric or not? Before looking at it.
Depends on what
Why?
you defined it
Why?
as. Is two people have talked to each other, or is one person asked the other a question?
I asked for people to fill a survey saying if they talk to somebody about a complexity topic during lecture, excluding announcements from
I
course.
expect if I talk to somebody, they talk to me.
So you would expect this to be symmetric?
But
If that's your definition.
Yeah.
But both people don't remember necessarily.
So yeah. So
So I just want to say, you make your point, except that like ideally there would be symmetric, but in reality, like there's a lot of noise in data. There are mistakes in our own like data recollections. We don't remember talking to people.
And yeah.
I also never got to go out.
Oh,
That's
sorry. Are you?
fractals why. But if you
You
just
can
take
put it
my
down.
points and make it symmetrical.
Oh yeah, you're an empty roll. Sorry.
Yeah, that's fine.
So what you just described as noise might not always be noisy. It might be something we're interested in, because sociologists that studies a group of people might be interested in these non-symmetric relationships. Because what you call discussion, somebody else might not call it a discussion. It was too short. It was just 5 minutes. It was a fast question. So depending on what we're interested into, this could be just something confusing our graph or something which we're looking for. And then we can see skewness and who is completely asymmetric. You talk to everybody, but really shortly and nobody cares about it. Things like that.
You can really see this in when people are asked to build like a friendship network, like, is this person your friend? And you
What
can
does that
really
mean?
see it there, that some people really are one-directional.
You have something in mind, Oana?
Now, you also have people are talking to themselves in one case.
Yeah, I think I do.
Yeah.
Sometimes. Again, it's a definition. Would you count talking aloud to yourself as talking to yourself, thinking about the complexity, or losing your mind, maybe? So let's go and calculate something. We discussed about the degree distributions, so I'm curious to see how this looks. And we said we can do a sum, so let's do a sum here. Okay, so this is the distribution. Do you have any expectations for how this should look?
Power law.
Why?
Why not?
Why not?
It's only like 1 order of magnitude, isn't it?
Yeah.
Any guesses why yes or why not?
Well, as Mark said, it's only 1 order of magnitude, so it's kind of hard to get to that kind of that variety.
Yeah. Any? Yeah.
I expect. I mean, okay, just without citing like the paper or something, but just conceptually, you'd expect only a very few amount of people to be very popular, and a very few amount of people to be unpopular. Sort of everyone in the middle, which is characteristic of power law, which is meaning that it sort of tapers off to 0 with the unpopular people, and then, well, I guess it would be this way. So I mean, it tapers off to 0 with the unpopular people, and then there's just very few. With that, a lot of things. I think I did that backwards again, but you get the point.
That's how you look at it.
Yeah, it depends on how you define your axis. So I would expect, but I guess interestingly, I would expect it to not be. The only difference is I wouldn't expect it to be a true power law, in that I would expect it to be like very few people with a lot of friends and very few people with no friends. So I would expect it to be kind of like a Gaussian. Yeah, I would expect it to be a Gaussian.
And I'd expect people to be different. There are teachers and there are idiots. I mean, students. And students, I would think, could talk less to each other, but a lot more to a teacher. So I'd expect two groups of numerics in there. So
There was one more comment somewhere from there. Okay, so this is a problem we would often come up with in real data. We have no idea what it's going to look like. There are some arguments for, some against. Let's try and think about the things that were mentioned before. So first, about the number. If we just have an order of magnitude, it's really hard to prove or to make sure that this is a power law because we have lower numbers. But we could have a real power law from which we sample just a few points, a small group, a subset. It would just be hard to test and get a significant statistical value. So probably with these data we have an intuition that it might be a power law from other similar type of networks, social networks we've seen before. But here the data are so few, the numbers are so small that probably it's completely confusing. Plus there is also the bias that we have two different types of nodes because we excluded the announcements we send through email, but still we do have lots of the emails back and forth for all the class stuff that we need to talk to people.
can you give us a plot of this number on log papers?
We can plot it up. I just wanted to say that first that this is the out degree. So we are going to do the same for the in degree because we just summed out the rows, and this is a directed network. Do we have any different expectations for this?
Yes. Ken's column will no longer be 0.
Do you think we would be able to fill out Ken's column just by looking at the in degree? I see nodding heads. Yeah. Maybe we should
Just by looking at what?
So we are missing a data row, but now we have a column. Can we say anything about?
If you just transpose it and then paste it back on to the row.
Because we assume this is mostly symmetric or very symmetric, or there's a high correlation between in degree and out degree, we should be able to fill out the missing data in this graph.
Can you scroll over so we can compare the two sums? That would be a good approximate measure of.
We're quite good.
The sums.
There we go, one more.
Very short and cabbage.
It is?
You could make a metric of how
You could
It's
even
pretty
subtract
nice.
one versus the other.
Pretty asymmetrical.
I'd like to take the difference.
I hear some suggested statistics. So one thing we could just draw a correlation of these two. The other thing is a difference, I think, is suggested. A
A
difference.
scatter
between
shot,
Yeah,
plot would
and
be the
scatter
same
would be it.
equivalent.
And also compare the variable distributions of both.
Yep.
Let's keep this for homework and look at the graph because we're getting short on time. So I can send you this. If you want, I can anonymize myself also, but probably. So let's look at how.
What did you use to plot those?
This is a library of called iGraph. I don't think we have time now to go through. I want to go through some software, but we'll do it next time. We can look at a few things you can use to study graphs and either visualize or do statistics instead of doing it by hand. So one thing in plotting is there are many different ways of showing a graph. So you can imagine, if we go back to our simple examples, just by pulling this out here, we show the same graph, but now we moved all of these things around. You know, so it looks somewhat different. So we can do this here. So there are many methods, many algorithms of trying to understand what is interesting and what is not. I have to admit I'm a bit surprised about how this looks. It would be easier to just eyeball some things here and do the rest of the examples here. So let me try to somewhat cluster them in a better way. So we might be able to calculate a few things.
What's the meaning of that format choice that you made?
There are many different ways to. So the simplest one is you can imagine every node repelling each other as if they have some sort of forces, and the edges pull them together. So if you simulate this through time, they're going to equilibrate somewhere, and you can pick different thresholds, and this would make dense parts of the graph to stick together, and others less. There are other ways of doing it at layers, as this one is. This could give us something about maybe instructors and different types of nodes. But that's a whole subject on its own. There are many different ways of doing it. So let's go back to our initial properties of the graph. I want to mention briefly some properties that we did talk about local and global properties, but everything was related to nodes. We can as well think about groups of nodes in a graph, and there are some things we might be interested to understand there. We mentioned in the paper with the clustering, one of those. One thing that you might be able to see here, but maybe not, so let's make an example that is simpler. So let's say we take a subsection of a class, and it looks somewhat like this. There is a part of the graph that is more dense and a part that is less dense. This is again a more or less local property, but it's not a unique property of each node. One important definition that we should mention here is what is a clique. So this is a fully connected graph. So all the nodes that belong to the clique are fully connected to each other. And this would be this part, the triangle. Everybody is connected to everybody. There might be some small groups. In pairs, there are obviously many pairs. In triples, there might be some fours, I'm not sure. At least the instructor should form a clique, so everybody should have talked to each other, if we completed this correctly. And maybe the people that do projects together, things like that. This is a very rough way of characterizing the network. There are many more subtle things, because if one of those are missing, but you could imagine having a fourth one here and then another group here. There are better statistics of describing the structure of the network. One method is finding where you could cut a network and break it up in two pieces. So here, I guess, if we cut this link or this link, then we have two disconnected components. This is called the minimal cut, and this could help you find what is the structure. So if we implement an algorithm that does minimal cuts, one guess would be that this could separate the class in two departments, or in undergraduates and graduate students, or some other more connected component, instead of just looking at cliques, which is more narrow. I mentioned the word connected component. This just means graphs that you can go from one node to another. So if we were doing the same thing in the beginning of the class, there would be groups that just haven't yet talked to everybody else. some individuals, pairs, and things like that. So all of these could be in our matrix. This is one connected component, this, and this huge one is another connected component. Actually, one other interesting thing is to tie back to the previous lecture, the size distribution of the connected components also in many real networks follows a parallel distribution. So we have one huge group of people that talk to each other, and then many, many smaller groups in social networks. So let's look at a slightly more sophisticated way of understanding what is the structure of a network. There's a concept of a module, which is a subgraph that has more connections within itself, among these nodes, compared to outside of these nodes. So let's look at an example. This part here, I'm removing the other components for now. So this here, just by eyeballing the graph, you could argue that this seems to be one module. But if we follow this strict definition, we can see that all of these nodes have more, 1, 2, 3, 4, 5 connections between them, and only one across. Does somebody want to maybe draw other modules on this simple example? Since you're next.
I think there's another one here, right? And,
What about cutting off one of those outliers? Question, I don't,
Yeah.
certainly, this has some connections, and here's an outlier which isn't as well connected.
Yeah.
I don't know if it's.
Any other suggestions? There are many modules overlapping. And this, you wouldn't call it an intuitive module, but according to the definition, it is a perfectly fine module. Any others? Except of skipping each one of those. Any other type of modules that you could skip? We could skip every single one.
Okay, we've agreed this one is also a
Yeah.
module. I'm not sure if the number there is sufficient to make this one a module.
These are not connected though.
Okay.
If they were connected, we could do that.
Okay.
But we could have this as a module also,
Yep.
and this as a separate one. Or this is a module, and this one,
What?
and
Okay.
one here, the remaining ones outside.
wait, how is this one a module?
Well, no, sorry, this is not. You're right. So there are many. Yeah.
Are some modules better than others? There's so many, but I don't like all of them. Like, they don't seem intuitive to me.
Let's try and see how we can group them somehow. So we could look at one level of module, these two. And this belongs to a larger module, which was this, I believe. So if we take these two and merge them with this, can form a module. So the immediate larger module, and this can form a module with this. So this can form a module with this. So one way would be doing it this way, and then these two form two large modules. And so what we did here is we clustered the modules by expanding slowly to include a larger and a larger one. And this could give us some sort of a more intuitive grouping of our system. We might choose to stay here, we might choose to stay here. Sometimes there might be some really important distinction if there's a scale in the modularity of the system. So if this was a social network and there was a scale of a class, then we would stop at the scale of the class and we could have more or less each class being a module. If the system is not, does not have a characteristic length, then there's no particular reason to stop at each. In general, detecting, this is also called a community structure because it seems to be, although it can be applied to other things that have nothing to do with social networks. There are many methods of defining many measures of isolating modules or classes or groups that might be more intuitive. For example, according to the definition, this seems a very silly thing to do, but if we just write an algorithm, it's going to find many of those. So it's considered one hard problem, and there are many different approaches to solve it. So one more thing about no more things. So let's wrap up. I'm going to send you a list of software which you can use for studying networks. And so everything we said today was just looking at networks without having statically, not changing them. But there are many interesting things happening through time. Networks change, evolve, build. So next time we're going to look at the dynamics of networks, and maybe in the beginning we will work a bit to familiarize ourselves with the software. I'm going to send you some links and instructions if you want to install some things on your computers, so it would make things easier. But please check it and send me an email if you have any trouble downloading and installing things. That's it.